Hey everyone! Next homework video that we're going to do for you this weekend is about measurement. I know that you've talked about measurement in at least 3 of your previous classes and probably 4 if you count biology. I believe they do some measurement stuff in biology. So this is stuff that I'm expecting that you already do know, but I wanted to make sure to give you a refresher just to make sure that we're doing it properly and making sure that we're handling things the way we're supposed to. If you can't measure properly, is that going to make or break your grade in physics class? No, it's not. But it's really something that paying attention to detail, things we should be doing properly to make sure that we're covering that stuff and make sure we're doing it good. One last thing before you go watch the video. I apologize, there's kind of some wind noise in there. It's been hot the past couple of days and the fans were on in the room. I tried to minimize it, but you might hear a little bit of like wind blowing kind of noises while you're watching. So anyway, hope you enjoy, and I'll talk to you at the end of the video. Okay, let's start off with why we have to do this. Why is it required that we spend a couple of days or even a week talking about measurements in science class? Because isn't it just reading the ruler? Well, kind of, right? First, where do all these numbers come from? In math class, you can just have 7, and it doesn't matter, where it came from. It's just 7, right? They write it in the book, you do the problem, great, good, right? But all the numbers that we use in science class are measurements. They're measurements of some aspect of the physical world, some aspect of the universe. That being said, that requires that we are all on the same page to make sure that when we're measuring something, we should get the same thing as somebody else that's measuring that same object. Why? Well, if we're measuring the same thing, we need to be able to see that we're talking about the same thing and that we're talking about it consistently. Where did that lead us? That leads us to the SI system. Not going to spend a huge amount of time talking about that, but SI system agreed upon by scientists to produce consistency in measurement. It's based on some aspect of the universe that is easily verified and always constant. So when we set up this measurement system, somebody decided that, hey, if we're going to measure with certain units, we have to make sure that my unit, when I measure it, is the same as your unit when you measured it. You may have heard of using like cubits to measure, or let's not use cubits. But if we talk about feet, not like feet that are on a ruler, but like your feet, right? Could you walk the length of the room that you're in right now, stepping heel to toe and counting the number of feet that it takes you to get from one side to the other? Yeah, you could. But if somebody else did that, they wouldn't necessarily get the same number. Now, does that mean the room is a different length? No. It means that our measurement tool, the feet or your feet that you use to measure that distance, aren't exactly the same, and therefore we get a different number. And that's something that we can't have. So what do we use? Different things that we know, that we believe at this point in time, based on our experience, based on our measurements, to be constant. For example, length. The meter is our base unit of length. A meter is defined as the distance that light travels in a very, very, very short period of time. But based on all of our measurements that we've made, based on all the observations that we've done, we believe that light travels at a constant speed, regardless of where we are in the universe. And therefore, we can use that fact that light travels at a constant speed in a vacuum, regardless of where we are in the universe, to say, all right, if I know how far light goes in this very short amount of time, it should be the same distance regardless of where I am. So we can use that to then measure other things. What's the next one? Time, right? We know from observations, from measurements that we've made, that molecules vibrate back and forth at a very, very fast, very quick rate. But it's a constant rate, depending on the conditions. So if we have the same conditions, if we reproduce the same conditions, regardless of where we are in the universe, we should see that those molecules vibrate back and forth at exactly the same rate. And because of that, we then count that number, or count the amount of time, measure the amount of time that it takes for that molecule to vibrate back and forth a certain number of times, and we say, okay, that should be the same amount of time regardless of where we are in the universe, as long as the conditions are the same. All right, stand by. Slide. Base units. Okay? Base units are the fundamental measurements that we use to describe an object. There are 7 base units, and I believe pretty soon here I'm going to show you a picture. I'm only really going to be, in this class, there's really only 3 that we use the most, and that's length, mass, and time. The base unit for length is a meter. We use lowercase m to abbreviate it. The base unit for mass is a kilogram, which is going to confuse a bunch of you. In this class, in physics, all of your masses need to be in kilograms, which I know seems kind of counterproductive. Why wouldn't you just put it in grams, right? It doesn't have a prefix. Gram is not the base unit. It's not the amount of mass that we measure everything else off of. It's a kilogram. So keep that in mind. From this point forward, anytime you see a mass, it's got to be in kilograms. If it's not in kilograms, convert it. And then the third one that we use most often in this class is time. And we use the second to measure time, and there's certain multiples of seconds instead of blah, 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 but we use length, mass, and time are the 3 things that we use the most in this class. Temperature, amount of substance, there's also a base unit for electrical current, but we don't get into those a whole lot in this class. The 3 ones that I want you mostly to be concerned with are length, mass, and time. Well, let's skip this one. We don't need this one. This presentation is from a different class. Come on. Mass and weight are not the same thing, and we'll get into that way more when we start talking about gravity, and we talk about forces and stuff like that. But let's get to, next, as far as units go. What we'll find in this class is that we can't measure everything that we want to measure using just one measurement. There aren't just a base unit that covers everything that we need to measure. Sometimes we need to combine 2. For example, speed, one that we'll use a whole lot in this class. Speed is a measurement of how far you went and how long it took you to go that distance. That's 2 base units, a length measurement and a time measurement. So we have to combine 2 of those base units in order to accurately represent what it is that we're measuring. And we'll see that we'll come across that very often in this class, where we have to combine 1, 2, sometimes even 3 base units in order to come up with a derived unit that accurately explains what it is that we're trying to measure. Sorry, just talked about that. All right, Y units. Hopefully you know this by now. Units are required on almost every number that we use in science class. There are certain things that we'll use in this class, certain numbers that are measurements that don't have units, and we'll talk about those and why they don't have units when we come across them. But almost every number that we use in science class requires a unit. Why? Because like we discussed at the very beginning, units are, the numbers that we use in this class are measurements. They're measurements of some aspect of the physical universe. If I have a number, I have to tell you what it is that I'm measuring. And I do that with the unit, right? The unit then tells me, okay, if I'm measuring a length, I put meters, and then everybody that's reading it knows, okay, I know it's a length distance, right? Seems elementary, and I hope that it is at this point in time, you being, in a senior level physics class, but worth repeating. All right, let's get down to the nitty-gritty of this, how to measure. All of our measurements that we come across are going to have 2 parts. There's a certain part, the part of our measurement that we know for sure, without any doubt. But then there's always the, stand by, uncertain digit. What is our best guess at the actual value of a measurement? There is no such thing as a 100% accurate measurement. All right? It just doesn't exist. I don't know how long that room that you're sitting in right now is exactly. And you'll never know exactly how long it is. There is some degree of uncertainty in every measurement that we take. And I hope that you understand that by now. We actually talked about it last week when we talked about sig digs. That's the reason why we have to concern ourselves with the significant digits. Because every measurement that we take has some uncertainty. If we then use that measurement to calculate an area, calculate a perimeter, whatever it is, that uncertainty in the measurement that we took is then carried forward in the calculation. The significant digits limits that uncertainty to a reasonable level so we can feel pretty confident in what we've got, but not certain. So there are 2 parts, certain digit, uncertain digit, right? Let's start off with, oh, just told you that, right? No measurement is exact. They're only as good as the tools that we use and the person using the tools. like I said, I will never know how long that room you're sitting in right now is. I can't know exactly. I can get a good measurement of it, and I maybe can know it to a greater degree of precision, but we'll never know exactly. All right, let's get down to why we're here. How to measure. So let's say I've got this ruler that's up on the screen right now, and it's broken down into centimeters, and then I want to measure this red line. Okay? So in your head, real quick, I'll give you like 15 seconds. You don't have to pause. You come up with a proper measurement for that red line. Then I'll go through the process. How long is that red line according to proper measurement technique? All right, let's break it down. First, I know for sure that that line is greater than 5 centimeters long, but less than 6 centimeters long. I can tell just by looking at it. It's definitely past the 5 centimeter line. It's definitely not to the 6 centimeter line. Therefore, according to this ruler and this line, I have one certain digit. I know that that line is 5 point something centimeters, right? One certain digit based on this measuring tool. But remember, we said that all measurements have two parts, a certain digit and an uncertain digit. What we have to do next is we have to estimate your best guess as far as how long is that actual line, or how long actually is that line. Remember, I told you you're never going to know, but we have to make sure that we estimate. And to me, that line looks like it's between about 70% of the way along between 5 and 6. So remember that we always estimate one digit, one decimal place, past what we know for sure. I know that that line is at least 5 centimeters long. I think it's about 70% of the way from 5 to 6, so I would record that measurement as 5.7 centimeters long, where 5 is my certain digit, 7 is my uncertain digit. If you wrote down, or if you in your head, you thought it was something different than 5.7, does that mean it's wrong? No, doesn't mean it's wrong, right? If you wrote down 5.6, if you wrote down 5.8, I'd give you credit for that, because in your estimation, it was only 60% of the way between 5 and 6. Or in your estimation, or according to your observation, it was 80% of the way between 5 and 6. That's up to you. Now, if you wrote like 5.3 centimeters, I might argue with you on that one, right? To me, it's definitely longer than 30% of the way between 5 and 6. But if we're close in that area, I'm not going to mark that wrong. Same thing on the test. If you're close, if we're off by one digit, if we both have one decimal place, but our last decimal place is different, I'm not right, you're not wrong, we're both right. It's just how we see it. New ruler. Notice, different set of measurements on this ruler. Notice on the very end, though, it's not the beginning of the ruler. That ruler goes on farther to the left of the screen and farther off the right of the screen than we can see right now. But this red line comes around, and there it is. We want to measure the length of that red line according to this ruler. So, once again, I'm going to give you about 15 seconds in your head or on a scratch piece of paper in front of you. What is the length of that red line according to this ruler? Go. Okay, let's break it down. Remember we said every measurement has two parts, certain digit and uncertain digit. Certain digit, in this case, I can tell by looking at that line. It is definitely past the 7.7 centimeter mark, but it is definitely not to the 7.8 centimeter mark. So in this case here, I have two certain digits. What changed? My ruler's different. I have more markings on the ruler. If I have more markings on the ruler, I can tell the length of that line to a greater degree of certainty because I have more definite markings of where certain measurements are. So in this case, I have two certain digits. I know that it's going to be 7.7 something. Now in my estimation, that looks like it's about 20% of the way between the 7.7 line and the 7.8 line. So I say that that measurement is 7.72. One place past what we know for sure. one digit past what the certain digits are from our ruler. Okay? Once again, you had 7.73, you had 7.71, we're good. You had 7.725 because to you it looks like it's 3/4 of the way, or 1/4 of the way between 7.7 and 7.8. If you write 7.725, right? Hold on. Just for emphasis. All right. Hope this works. Right? If you write 7.7 because you know that it's longer than 7.7 but less than 7.8, but then to you it looks like 1/4 of the way between 7.7 and 7.8, so you write 7.725, right? Because 2.25 is 1/4 of the way, right? Wrong. We can only have one digit past what we know for sure. So in this case, the best we can do is to the hundredths place. I can't take it to that thousandths place, even though to me it looks like it's 1/4 of the way, and math class told me that 1/4 is 0.25, right? Doesn't work that way when we're making measurements. You can't have that extra place. So, to summarize, number of certain digits is going to vary depending on what measurement tool we have, and more specifically, how many marks that measuring tool has on it. We can't add the extra decimal place unless there are 10 marks between the previous known measurement and the next known measurement. If there's 10 marks, then we can add the extra decimal place. If there's not, we can't. Okay? But there is always only one uncertain digit, an estimation of how far it is between the previous certain digit and the next certain digit. That's actually part of your measurement. It's the uncertain part of your measurement. It's not the actual length or the actual mass or the actual volume, but that uncertainty is part of how we measure. Okay? So certain digits will depend on the number of markings on the ruler that we're using, whatever measuring device it is, but there's always only one uncertain digit. Together, the number of certain digits plus the number of uncertain digits, that tells us how many significant digits a measurement has. And we talked about that last week. One more practice. Take a look at the screen. This is not a length measurement, it's actually a mass measurement, and most of you have probably used beam balance before. So I've moved my beam balance, and I've moved the little slider on my beam balance to put it in this position to balance out the masses that I have. So take 15 seconds, look at the markings on the beam balance that you're seeing right here. Even though they might not all be marked, look at the markings and determine what that value of that mass is. Each line on this balance represents 0.01 grams. Notice that the 7.1 gram line is marked and the 7.2 gram line is marked, but if you count, right, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That distance between 7.1 and 7.2 has been broken up into 10 equal divisions. And that means that each one of those lines now represents 1/100th of a gram, because we can go that extra digit if we have the 10 markings between the previously known and the next known. Right? So that means that for sure I know my mass is greater than 7.10 but less than 7.11. So now I have 3 certain digits. But our measurement isn't complete until we add that uncertain digit on the end of it. And to me, it looks like about halfway. So I'm going to say 7.105. 3 certain digits, 1 uncertain digit, 4 total significant digits, proper measurements. Next one. Take 15 seconds. Go over it. All right, same measurement device. So we know that the divisions are exactly the same. So I know here, this really appears to me to be on the 7.16 line. Okay? It really looks to me that it's right on that 7.16 line. Some of you might argue that, and that's okay, because there's uncertainty in measurement, right? But to me, it looks like it's exactly on the 7.16 line. But if I just write down 7.16, right, I don't have the same number of significant digits as the previous measurement that was taken on this measuring device. That's a no-no. If you're using the same measuring device to measure different lengths or different masses or different volumes or different times for that matter, your measurements taken with the same measurement device should have exactly the same number of significant digits as anything else that you measured with that measuring device. That's how measurement works. So if I only write down 7.16, that's only 3 sig digs, whereas my previous measurement had 4. If it's exactly on a line, you gotta tell me that. And we do that with the 0 at the end, right? 7.160 means to me, I looked at that measurement and I thought, that measurement is right on the line. It's right on the division point, okay? But remember from our sig dig rules that if there's a decimal point and there's a 0 at the end of that measurement, that 0 is significant. So this number has 4 significant digits, just like the previous measurement. 2 terms that you should be familiar with by now: accuracy and precision. Accuracy is the closeness of a measured value to the actual value. What is the actual value? Up to just some debates, but there's usually a accepted value or a value that we all sort of agree on that, yeah, that's what it is. Okay? On the other hand, precision in measurement is the closeness to a bunch of measured values to each other. So if we're all getting the same thing, all of our measurements are precise. Okay? Now, sometimes we use precision as well to reflect the number of certain digits that we have based on the measurement tool that we have, that we're using, right? If we add another decimal point because the markings indicate that, generally we say that that measurement has more precision or a greater degree of precision than a previous measurement. Don't get them confused. Same word used different ways. Okay? But we can have some errors in measurements. Could a measurement be precise but not accurate? Yeah. For instance, if we're throwing arrows at a dartboard, right? Or darts at a dartboard, whatever, unless you're into archery, I guess. Okay? We keep throwing the darts, and we keep getting them in the same spot, but it's not close to the bullseye. We keep getting the same measurement over and over again, but it's not the accepted value. We would say that those measurements are precise. They have good precision because they're all next to each other, but they have poor accuracy because they're not close to the accepted value. What would lead to something like that? If something's wrong with our measurement device, we're all reading it properly, we're all getting it to the same number of significant digits, we're all getting values that are very close, but they're not close to what they're supposed to be. Generally, that means something's wrong with your measurement device. On the other hand, if, using our dartboard analogy again, right, we're throwing darts at the dartboard and we're hitting the bullseye and we're continuing to hit the bullseye. Good accuracy because we're where we're supposed to be, good precision because they're all close together. Generally, that's what we're striving for when we got our measurements. All right. One last thing before I close it out here. All right. I've got a couple of things for you to practice. Okay. So I'm just going to, hold on. Sorry if it's making you sick. I'm going to give you a couple opportunities to practice. Some length measurements, some temperature measurements, and some volume measurements, just to give you some practice, okay? I'll go through and explain why I wrote what I wrote as we go along, right? So here's your first length measurements. Measure the length of that copper strip that is above the ruler, based on that ruler that's there. All right, so if I look at the length of this copper strip and I see where it is, and to me, it definitely looks like that copper strip is past the 12.8 line, but not to the 12.9 line. So I'm going to say this is 12.8 for sure. 3 certain digits. Okay? And then I take a look at it, and it looks, I don't know, maybe about 30% of the way, right? So 12.83 centimeters. Okay? I know it says millimeters here, all right, on this ruler. Each one of these little lines is a millimeter. 10 millimeters is a centimeter. So don't get confused, okay? So 12.83. Is that the only acceptable answer? Absolutely not, right? 12.84, 12.85, 12.82, any of those will work, all right? Is 12.8 an acceptable measurement? No, all right? We got to have the same number of significant digits on our measurements in order for it to work out for us, all right? Next, same gold strip, 2 different measuring devices. I'll give you a couple seconds in your head. Figure it out. What would be the measurement using the top ruler? What would be the measurement using the bottom ruler? Go. Okay, so looking at these two measurements, right? It's the same length, but because we're using different measuring tools, we don't get the same representation of that length. The top ruler has more divisions, therefore it has more certain digits, therefore it has more significant digits, right? 8.69 based on where we are. Is 8.69 the only acceptable answer? No, it's not. Okay? But on the bottom one, right, we only have markings at every 1 centimeter. So the certain digit is only this place, right? The uncertain digit is one past what we know for sure, so that'd be 8.7 centimeters. Once again, not the only acceptable answer. All right, so let's move on and let's take a look at some thermometers. Okay. Thermometer on the left, tell me what the temperature of this substance is. To me, 32.7. Definitely greater than 32, definitely not 33, one place past what we know for sure. Make sure you look at this thermometer closely. All right, so this thermometer, right, the big markings represent 20 and 21, but there are 10 divisions between the 20 mark and the 21 mark, which means we add another level of certainty to our measurement, right? That takes us out here to the tenths place. Each one of those small lines represents 1/10 of a degree. So we know out to the tenths place for sure. Estimate that last digit. I think it's right on the line. You might argue and say it's 20.21, whatever. We're both right. So there we go. All right. Last practice, 2 volumes. Remember, hopefully you remember from chemistry class, when we're measuring volume, let's measure to the bottom of the meniscus. And that's what I got. Only acceptable answer is no. But once again, if we look at the divisions that are on these different graduated cylinders, right? If we look at the divisions there, different degrees of certainty, right? The first graduated cylinder only has 1 milliliter markings. Therefore, we can only go one place past the 1 spot, so to the 10th spot, right? But the graduated cylinder on the right has markings at the 0.1 milliliter mark, so we know up to this point for certain, right? And then one place after what we got. Okay.
All right, everybody. Hopefully we got measurement down now, and we won't have to talk about it anymore throughout the year. Just a quick heads up as far as what we're doing this week. Tuesday, when you get into class, I have an activity for you in class that involves measurement, also then taking the next step and using those measurements to do some calculations, get you some sig-dig practice there. Wednesday, first block day of the year, we're going to go around the school and make a couple measurements in different places. One of those places being outside. The weather is supposed to get a little bit cooler next week, so keep an eye on that. You guys do have it first period, 7:30, or actually now it's 7:55. Sorry, got my times wrong. But anyway, so make sure that if it is a little bit cooler in the morning, you bring yourself a sweatshirt, or if it's wet outside and you might have to go in the grass, make sure you wear some shoes. Then on Friday of next week, we'll be back in the library making some graphs out of the data that we collected on Wednesday during block day. Also, you'll have a short quiz over measurement on Friday at the beginning of the period. Hopefully now that we got the graphing stuff down, we can get all that stuff done on Friday. You can turn that assignment in and you'll be good to go. If you're looking ahead, we are looking at tests, I believe, the following Tuesday, so a week from the day that we get back. I'll give you a heads up on that in class, but just giving you, a little bit of foreshadowing. That was the word I was looking for. Anyway, enjoy the rest of the weekend. I will see you on Tuesday.